Welcome to the Bloomberg Learning Machine Seminar Series. It's a pleasure to introduce Dan Roth from University of Pennsylvania for our first speaker this year. I think it's a great start. So Dan is a fellow of the AAAS, the ACM, the AAAI, and the ACL. Over the years, Dan worked on, I think, basically every problem in NLP machine learning and general AI, and contributed immensely to the field. To know the specific achievement that really transformed how we think about things is the introduction of interlinear programming that was from Dan Roth and his collaborators. It's really allowed us to think about global inference in a completely different way. It really changed how the field thinks and gave a lot of people the language to talk about inference that was really lacking before. And of course, something really important is that a lot of the work that Dan did is not only just constrained into uninterpretable code that is in the lab, it's also matured into one of the most comprehensive toolkits for natural language processing. So Dan, I'll let you continue.
Thank you. Thanks a lot, Yoav. Thanks for coming. So I want to talk about what I call incidental supervision and what you will call after this talk incidental supervision, I hope. And I'm going to mention talks by many students, postdocs, collaborators. And before I start, so Yoav already gave an introduction, it's better than I can do, but just to give you an idea, so my group has been working over the years on a range of things that I think are important in order to make progress toward natural language understanding, from what is called methods or frameworks of how to do learning and inference in natural language processing, how to incorporate knowledge, how to think about inference, and also how to think from a principal perspective on machine learning for natural language processing. We've worked on a range of problems in natural language understanding or information extraction. You can think about them either as those problems that drive the development of methods, but also as a way to investigate whether the ideas that we have work and how well they work. A range of problems from textual entailment through semantic language models, through temporal reasoning, quantitative reasoning, what have you. Not all the problems, but all the problems that I thought were important, including multilingual NLP over the last few years, including computational issues like amortized inference, and over the last few years also problems in an area that I called information pollution or information trustworthiness. And we have developed tools, so please take a look if you need any components for your NLP pipeline. So I'm going to talk about a small slice of these things from a specific perspective of supervision or lack of. And I'm going to start with asking you to read this slide. Nice to meet you too. So people get this in seconds. I assume you haven't seen this before. And it's not clear to me how come people do it so fast. I don't know how to write a program that does that. But if you think about it, it's a really involved problem. And I think about it really as natural language understanding. So what do you have to do in order to understand this? I mean, you have to identify units. You have to consider multiple representations. I mean, there's images, there's characters, there's different representation and different positions of them. Each one of these components has multiple interpretation if you put it in isolation. But when I put this together on one slide and I tell you that there is some interpretation, you get it within seconds. And you don't care whether it's pictures or text or other things. You know how to put this together with the appropriate interpretation and determine what is the best interpretation under some definition of best. Something that satisfies your expectation. And I'm using keywords that I'm going to repeat later on in the talk. So to me, as I said, this is really natural language understanding. So I think about natural language understanding as making global decisions that require making a lot of local decisions, using a lot of local predictors that are driven by different things, trained in different conditions, different times, different people, different scenarios, it requires the ability to put these things together in a way that makes sense, coherently, and it requires knowledge that guides the decision so they satisfy our expectation. And really the two keywords here for me are coherently and satisfy expectation. So expectation is a knowledge-intensive component. To have expectation on the output, you have to know things. And my goal in this talk, in some sense, is going to be to tie the notion of expectation to the notion of learning. So the thesis that a lot of my research works under is that natural language interpretation is really an inference process that is best thought of as knowledge constraint optimization problem that is done on top of many statistically learned models. But in order to be able to learn, I think that the notion of expectation from the output is key, and this is in some sense going to be what I'm going to talk about. So what is important in order to make progress in this? I'm going to mention three things that I think are crucial. One is learning and reasoning in the presence of knowledge. So we have to be able to combine the soft nature of natural language with the logical, declarative, structural nature of language. And we cannot do this without knowledge. So knowledge is really an essential ingredient for effective machine learning. The second component is we have to learn, we have to train models. And I think that an important aspect of thinking about training model is that of incidental supervision. I found this nice logo of creating incidental learning opportunities, which is actually a good description of how I think about we need to supervise models. And there's a third component of scaling up in terms of computational scaling up and in terms of dealing with many, many phenomena that natural language understanding consists of. So today I'm going to focus on one of these things, just on training model with incidental supervision, and I'm going to try to describe what it is and convince you that this is an important perspective to think about. So our goal is really to induce semantics, right? So inducing semantic representation that will support making decisions. And clearly this requires learning and in turn requires supervision. So the standard way machine learning works, and this is not only in natural language understanding, this is in computer vision, this is in many other areas. You're given a task, you collect data for the task, you annotate it, and then you learn a model. And it doesn't matter how you do it. So a few years ago you used linear models, nowadays you use your favorite neural network, but this is besides the point. The key issue is that you're doing it task by task, you collect data and you annotate the data. And I think that we will never have enough annotated data to train all the models for all the tasks we need this way. In fact, we don't know even what are all the tasks. So if you really think about it, most of what you learn, perhaps modular perception, you don't learn this way. You learn by reading, you learn by being told, you learn by being exposed to things, you learn by inferring things, and not by being exposed to many annotated examples. So this methodology is not scalable, often makes no sense. I mean, you can think about any complex task in natural language understanding, think about events. We kind of agree about outcomes of events, what happened, when did it happen, and so on. We hardly agree on the intermediate level, the spans, and other details. So really, we have to think about a slightly different framework. So I would argue that in most interesting cases, learning should be and is driven by incidental supervisions. And I'm going to try to explain what I mean by that. So data provides a lot of hints. Data that exists independent of the task at hand or the tasks at hand. And these hints often are sufficient to infer supervision signals to a range of tasks. So utilizing these hints can be less costly than producing explicit annotation. It's more realistic. It provides signals for tasks we haven't defined yet. And this happens all the time if you think about natural language understanding. Whenever you really work on a problem, you discover that there's a lot of tasks that the community hasn't identified yet, but you actually need to solve in order to make progress. And of course, this will give you some weak signals that we will be able to, or we should be able to amplify to produce higher quality signals. So I will try to argue that the strength of these incidental signals is really a function of our expectation from the output, some knowledge that we have about what's about to happen. And I'm going to start by giving you a few examples. Here is a short paragraph, and you can see, you can read it, you can see that Chicago is mentioned there. Keep on reading, and you'll see that O'Hare is mentioned there. And if you didn't know, you now know, I think, or you have pretty good reasons to assume that O'Hare must be in Chicago. How do you know this? I'm not sure exactly how you do, but it's something that has to do with your knowledge of how text is being written, conventions of writing text, discourse, and so on. And even if you didn't know this fact, now either you know it or you have some pretty good idea that this is likely to happen. So in general, supervision could be incidental, but identifying these supervision signals could be challenging. So I'm going to give you another example that isn't so trivial from the domain of transliteration. So transliteration is the problem of writing names in other languages. So how do you write Hussein in Russian? So of course you can make this a supervised learning problem. In order to solve this well, until a few months ago you needed a couple of thousands pairs of names, but can you do it differently? So let's assume that I have a comparable corpus, not a parallel corpus. So think about the BBC. The BBC writes every day news about the same topics in about 50 languages. So I can think about this as comparable corpora across languages. If I know how to write Hussein in English, which I do, I can look over time over the temporal profile of how many times Hussein is being mentioned every day or every week. And then I can look in another language, say in Russian, and I want to look for signals that temporally look the same in terms of frequency of occurrences. It's very likely that Hussein will have exactly the same distribution or very similar distribution. Other words, like Germany, will have different distribution. Of course, there's no guarantee because there could be other entities that are highly correlated with Hussein, like Iraq, that will also have similar distribution. But this is going to give me a very strong signal to the fact that these two strings actually are translation of each other. By itself might not be sufficient. Maybe I will need some other weak signals like phonetic signals, context, topics, and so on. But together I will be able to get more robust signals. Of course, I need more than just thinking about signals. I need also some idea of how to do inference, how to put together these signals. So this is an involved example. I can give you simpler examples. Let's assume you want to build a gender classifier. So given a name, you want to be able to know is it male or female. Let's say in English, let's say in other languages. How would you do this? Ideas, yeah?
You set a list of names and you write down the genders of that name in each occurrence, and you just train a normal machine learning model.
So you can do exhaustively, ask all your friends, give me names of male, female, and then you generate a data set and you'll train. Okay.
Well, I mean, it depends on the language too, I guess.
Depends
Some
on the
languages
language.
might be predictive that, ends in something, is a female, ends in something.
Slavonic languages end in A.
In some languages, you get some clues from the morphology, but still you have to know this, right? Yes?
Couldn't you just look for proximate use of pronouns in?
And that's a much easier signal. So I can go to Wikipedia in any language that you want, and I'm going to look at gender pronouns and count them and decide by majority. And that's going to give me a robustly, with accuracy of 99% or so, modulo names that do not determine gender. And these exist, but not too many. So here is a very simple signal. It already exists in the data. You didn't have to do any work. Here are some other examples. Images. It's difficult to label objects or to label faces, but it's very easy to learn same or different signals from images. For example, if I show you an image and it has multiple faces, they are different. If I show you this as part of a video, 2 consecutive frames probably represent the same object or faces. So it's very easy to get some signals that are highly correlated with what you care about, very hard to get the real one. And these kind of things exist in many, many cases. So when I talk about incidental supervision, again, I'm talking about the fact that there's a lot of information in the data itself that exists there independent of the task, and the question is, how do we exploit it? So I want to talk about it from 3 different perspectives. One of them is representation. Often making predictions is really all about making good representations. The second one is going to be about signals and structures. How can we exploit weak signals and put them together via expectation that we have from the text? And I'm going to finish with some ideas on behavioral level feedback. So I'll present a few new and some old research results from this incidental supervision perspective, and I'm going to try to share with you some initial thoughts toward the theory for incidental supervision. So let's start with representation. So I'm going to start with the simplest problem I can think of in machine learning, and that is the problem of text categorization. So here's a piece of text. You know what this is about. You know it's about sports, it's about tennis. Here's another piece of text. You also know what this is about, right? So this is about money, about healthcare. Now, how do we deal with it today? Traditional text categorization requires that we train a multi-class classifier. We train it with labels that are called 1, 2, 3, 4, up to K. Someone needs to label the data, and all your model knows once we've trained this multi-class classifier is to classify into these K labels. Can we do otherwise? I mean, can we do it, can we label or place a text document into any given taxonomy of categories without training on the label data? Now, you can do it. You just did it when I showed you this example, and the reason you did it is because you have some understanding of the labels. And in fact, we can do this. So essentially, what we're talking about is, given a single document, given a taxonomy of categories, what I need to do is I need to be able to map my label, set of labels, into semantic representations. I need to be able to map my document into the same semantic space. And once I can do this, it's a simple argmin problem given my distance function. Let's say cosine or something like this. So that's a very simple thing that all it requires me to do is to find this representation. Now, before I continue talking about it, this is not unsupervised learning, if you think about it. So unsupervised learning really requires that we make some assumptions on a coherent collection of examples, assumptions that say that if you have similar data points, they are mapped to similar labels. In this case, I'm mapping a single document. I don't need a collection of documents. It's more related to zero-shot or one-shot learning. I assume people are familiar with this. Again, it's not exactly the same because zero-shot, at least the way it's defined in most of the literature, you have a multi-class classifier, you train it on some of the labels, and you hope that it will generalize to label you haven't seen. Here I didn't do any training. All I did is I showed you some categories, and I told you, given a document, map them into one of these categories. So we call this dataless. The name didn't catch, so we're calling it zero-shot now, even though it's not exactly the same, but you choose what you want to do. Now, if you do have a collection of documents, rather than just a single document, you can use this and then bootstrap from it. But still, the key technical difficulty is, what are good semantic representations? And there's a lot of work over the last few years on semantic representation. We actually find that in the context of text categorization, the best results are really not dense embeddings that people swear by today, but rather sparse embeddings that are called ESA, for extended semantic analysis. Wikipedia-based semantic representation that basically say that for each word, I'm going to represent it as a sparse vector of all the Wikipedia titles where this word appears, weighted with TF-IDF, for example, or something like this. This is a very powerful representation that is very hard to beat. But regardless of that, this is a task-independent representation. That's the focus of what I want to say. Even though we augmented it recently with some task-specific representation, I'm not going to talk about it. The issue is that this is a very powerful representation. In fact, you can even do multilingual document classification. So I can give you documents in other languages, all Wikipedia languages, and because Wikipedia has cross-lingual links, I can actually generate this representation across languages. And for languages for which the Wikipedia is rather large, like Hindi, we can get very good results. Understandably, if the Wikipedia is very small, we can't get good results. But the bottom line is that you can actually get, just by mapping into some good representations, pretty good results here. And you can extend this to more interesting phenomena. For example, events. So what do I mean by event? Here is a piece of text, the event of attack here. So I have a trigger for the event, but I also have several arguments for the event. So an event is not only the type, but it's also a collection of arguments, so it's a structure. And I should be able to represent, using the same idea that I mentioned before, a structure in exactly the same way. So I'm going to use semantic or labeling, for people that know what it is, as a way to identify this structure, and then do the type classification, just like I mentioned before, and then represent components, arguments of this event using multiple representation, from Word to Vec, through ESA, and Brown cluster, and so on. So essentially what I have as a representation of event is this vector representation. What does this allow me to do? For example, it allows me to study relations between events, again, with no training whatsoever, once I have my representation. So I can think about a simple distance metric between these representations, say cosine, and this allows me to solve the coreference, which means, is this event the same as that event, within documents or across documents? When you look at these things, and I'm not going to give very many details of experiments, but you can see that this zero-shot approach, the blue one, is not as good as supervised approach when you're working within domain, but once you're working across domains, you train your supervised model in one domain, but you evaluate everything on other domains, you actually get significantly better results from the zero shot, which is hopefully clear, because these approaches will not overfit, and they're going to be they're going to support transfer much better. So to summarize, I mean, these learning protocols really rely on the ability to generate good representations, and you can do this in many, many tasks. So we've worked on text categorization, on events, on wikification or entity linking, relation identification, and so on. And in all cases, one of the key benefits of learning this way is adaptation or transfer. One key that I want to mention is there is a broad use of embeddings today in almost all machine learning communities and applications, but one thing that people don't do enough, almost no use of the task or the label understanding as a way to do better learning. So even in the case of text categorization, people do use embedding to represent the documents, the X, but they hardly use representations to represent the Y, the task. And I think that's really important, because this is where you bring knowledge into the problem. So I'm going to give one more example under this representation category. I'm going to talk a little bit about open domain zero-shot entity typing. Yeah.
Question before? So how much data, I don't know if it's a bit, need to think how to integrate it, but how much of the training data you need to outperform the supervised system?
Okay, good question, in fact. So we answered this question in the context of text categorization. So we beat supervised learning if you train with between 1,000 and 2,000 labels per category. Once you have more than 2,000 per categories, it's much better than what we can do with our dataless approach.
So you try the other way? Is there a way to take, let's say I have 10,000 examples in the supervised examples. That's my supervised training data, and I'm going to use 20 supervised examples, somehow mixed with the zero-shot approach. Can I outperform the 10,000? Because the results were so close.
So we haven't done this specific example. We've done it in the case of events where we show that 5 prototypes, for example, give us a boost. But this actually is not a kind of a clear-cut result. It also depends on how many labels you have. So now we are playing with a case where we have a few hundreds, like say 500 labels, and we're beating, we actually don't know yet how many examples we need, for example, to train RNN on it, because the ESA representation beat it quite handily for this. So it's the right question to ask. You know, eventually, with enough supervision, you're going to beat these methods. But maybe a little bit of supervision is going to save us here. Okay, so please feel free to ask questions as I go. I want to give another example, which I find interesting and very recent. So, and this is the problem of entity typing, and specifically open entity typing. And by open, I mean give me a new taxonomy of types. I want to be able to type entities or noun phrases into it. So here's the problem. Given a sentence, given a mention, and a taxonomy of categories or types, label the mention with a set of types. So here's a piece of text. I want to be able to know that UW is an organization. Specifically, it's an educational institute. Department of Chemistry is an organization. Specifically, it's a department related to education. AAAS is an organization. Now, you knew that even without the context. I could just giving you these strings and you know it. But in this case, you don't. Bruce Robinson, you probably know it's a person, but you don't know who this guy is, I assume, and there are many Bruce Robinsons, so you need the context. In this context, you know, okay, I knew it's a person, now I know this guy is a scientist. So there is a mix here of context plus just knowing some stuff. And there's been a lot of work over the last few years on this problem. In fact, started earlier, but no one noticed. And there's been a lot of comparison. I'm not going to go into this table. The only reason I show it is because almost all the approaches that people have used use training. Training on the specific data set with the specific taxonomy, which requires a lot of annotation. And it requires also thinking a little bit. So almost all this training is done with something that is called distant supervision, which is actually an interesting notion. I'm not going to define it here. I'm hoping that you know, if not later on, search for it. But it's a little bit misguided in this context. And the reason I think the distant supervision is misguided here is because the way people do it is they do distant supervision from Freebase, for example, Wikipedia, if you don't know Freebase. Now, Obama there is listed with many, many types. He's an author, he's a lawyer, he's a politician, he's a father. And therefore, distant supervision is going to tell you that whenever you see Obama, he has all these types. But in a specific context, it could be only a father. Obama took his daughter to lunch. I don't know that he's a politician now. So unlike coarse name entity recognition or coarse typing in general, where the context is everything. If you look at under the coarse grain, you'll see that in 84 or 90% of the cases, what is the type can be inferred purely from context. This is not the case when you want to do fine types. You want to know that Obama is not only a person, but you want to know what is the type expressed in this context. You need to actually know, in large percentage of the case, who is this person in order to figure out what is the type. So we need to know more, and we need to know whether we know. Is this the right Obama? Is this the right Bruce Robinson? So the approach that we are proposing is zero shot, in the sense that there's no task-specific training, and it's open in the sense that give me a taxonomy, we can classify into this taxonomy. We use multiple resources, wiki links, pre-trained Elmo model, which again is not defined in a task-specific way. You can train it today, you can do many things with it. And Wikipedia, specifically we take from Wikipedia what is called the surface title probabilities, given a surface, what is the most probable title linked to this surface. So what information can we get? So we think about types as containers that bind entities together to form a coherent group. And then we say that two entities are type compatible if they share at least one type. So the approach given that is that given a mention in a sentence, we discover type compatible entities in Wikipedia and then infer the mentions type using all these type compatible entities together. So what is the task knowledge that we bring? Kind of like the labels representation in the case of text categorization. We define type as a collection of entities having this type. When you show me a piece of text, I'm trying to think about who might share types with these entities that I discover here. I can go to Wikipedia to find who may share type with them, and this is how I'll decide what is the type. So again, Wikipedia provides very rich information. It was put there independent of the task we want to solve, but it's very helpful. So the key idea really is this type compatibility, and we discover it by this notion of context consistency, some distance metric that we infer using Elmo representation and ESA representation. I'm not going to give the details, but at a high level you can think about it. So this way, so if the probability of a concept title in Wikipedia given the surface is very large, I know who this guy is. Otherwise, I'm going to use ESA to map mentions to candidate Wikipedia concepts. Oh, and in this case, I'm going to use ESA to map mention to candidate Wikipedia concepts. Otherwise, I'm going to look at context consistency and try to find many compatible mentions. For example, I'm looking at this green piece of text here, and I see this person that I can't even read the name, Ornius, the UW leading scorer. I don't know who this guy is. I'm looking at the context, and I'm going to find a lot of other type compatible entities, maybe 20 or 30 like this, and I'm going to use them to infer that this guy is a person and an athlete. So what's interesting about this approach? Of course, you can beat it. These are the results that we get, and you can see that the diagonal dominates us. So if you train on a specific data set, you can do better. But on the other hand, we come second best on all data sets without doing any training. And similarly, and even more impressively in some sense, on a problem of coarse typing or name entity recognition that has been engineered to death, you can see that, again, we do not beat the diagonal. This is a comparison with our own NER, that is a state-of-the-art NER. On a specific data set, our trend NER beats our system, but it gets impressive results without any supervision whatsoever. Basically, with this idea of type compatibility and similarity between representations. So again, the key thing to notice is this approach gives good transfer across domains, across taxonomies. Okay, so far I talked about representation, and I want to move to talk about signals in general and structures. So I presented quite a few examples already where the signals are correlated with the task, and I argue that I can use this to replace supervision. Now you can ask, is this an art? I mean, okay, you invented this pronoun gender idea, or this similar or different, or this temporal thing, or many other things that we've done over the last few years. can we develop a theory that supports it and give us some guidance of what should we do, what's important and what's not? So that's what I'm going to try to do now. In many problems, I would argue it's very easy to get some good signals, high precision signals, but difficult to get exhaustive annotation. You will not get a lot of annotation. I'll show that this is often good enough, and I'm going to show this theory or develop the theory in the context of partial annotation of structures, but argue that this goes a little bit beyond that. So let's start with this example from low resource name entity recognition. So here is a piece of text in Romanized Bengali. Hopefully not many of you know Bengali, but some of you can recognize some entities here. Can you recognize the name entity?
No.
Palestine is there. Another one? Wow. Very good. Another one? Gaza is there. And these two you can do. Many people manage to do this. There are two others that are very hard. This is ABC and Gillian Findale. But many people can get Palestine and can get Gaza. So I think non-native speakers can provide low recall, high precision annotation. They cannot provide exhaustive annotation. So the question I'd like to ask here is, will this be enough? And I'd argue that actually it is enough. And the reason is that we have strong expectation from the output. For example, we know that immediate neighbors of entities are non-entities. We know something about punctuation, numbers, non-entities. We know that names have low frequency. This is some kind of a global expectation that we have. Specifically, it turns out that the ratio of entities to non-entities is quite stable across languages. It's about 10%. So I have these global expectations, and I would argue that these very few sparse signals, along with global expectation, actually limit quite a bit the flexibility they have in annotating the other things. So I have expectation from the output, which you can view as constraints on the unknown annotations. Here's another example, temporal domain. So we've done a lot of work in the temporal domain over the last few years. It's really an interesting domain. What do I mean, work in the temporal domain? Here is one example. There are multiple events here, right? And you can see them in red. And I want to be able to timeline them. I want to understand the relation between them. What's before, what's after, what's included, and so on. So it turns out that this is a very difficult task. Even annotators that we pay in order to do it don't do a good job, and they typically, because if there are n events, there are n square edges that they have to think about, and they don't. They only go with a small number of them, and they leave the graph like this. So really they annotate it only partially. But again, we have very strong expectation from the output. So I would argue we can live with this. What are the strong expectations? One of them, for example, is transitivity, right? You know that if A is before B, B is before C, then A is probably before C. But there's more. I mean, some events tend to precede others or follow others. So we have one of our works in NACL this year showed that we can build a knowledge base where for each event we can develop a distribution of what's likely to come after it, what's likely to come below it, or a distribution over things that would come before it or after it. So these are constraints that everyone is aware of, or my system is aware of, and this limits what can be on this edge. Not everything that a priori could have been there can be there now once I know some of the relations. So really there are two research questions if you want. So one of them, so this intuition, what impact does it have on the level of supervision needed? And of course, there's the algorithmic approach. I mean, how do I gain from this? So let me try to formulate what I'm talking about here. So we're talking about structures. People that are familiar with structure prediction would be comfortable with this. Otherwise, it's basically a structure is just a collection of random variables, y1 to yd. And by C here, what I denote is the set of constraint output. Not everything is possible because I have some constraints. Some output, some combination of y1 to yd are not possible as output. So Here is an example of a graph with complete annotation. In this case, I care about the edges. The nodes are given to me, the labels are on the edges, and I have 2 types or 3 types, or in the real data set, 6 types of edges. So in this case, my D is going to be 6. So 2 trivial cases that you can think of just to kind of make sure that we're talking about the same thing. You can think about all the variables are independent. There's no structure at all. I just drew it as a graph. And in this case, the set of outputs is just going to be the size of my vocabulary to the D, L to the D. No, completely independent. Or you can think about the other extreme where the structure is so tight that once you know one of the labels, you know all of them. For example, in this case, all the labels are the same. So this is another extreme case. So the idea is that if I give you a complete annotation, I determine a unique point in this C of L to the D. In most cases, I'm going to give you a partial annotation, and there what I have is a subset of configuration that is still possible. This subset of configuration should contain the true one, and I'm going to denote by Fk the size of the subset if k out of the V variable are already annotated, are already labeled. So this is the case here when I've labeled a few of them, and I have, I don't know, dealing with F4 or something like this. So with this, I'm going to define this ik, which is going to be the log of my output space minus the expectation of log fk. The reason I need to talk about expectation here is because different k labels could lead to different fk, which in itself is an interesting question because maybe I can think about different policies of which k do I want to label, because I want this fk to be large. But let's forget this about now. I care about this ik because really it measures how much of my output space has been disqualified by these k labels. Let's take again these 2 extreme examples. If all the variables are independent, there's no structure, then it's very easy to see that ik is just k log size of L, and therefore ik minus 1, the gain that I have when I added one more label is constant. So everything I do is the same. On the other hand, if there's a very tight structure, then again you can do a little algebra and you'll see that I0 is going to be 0. But for all k after it, it's going to be the log of the size of L. Yes?
Sorry, why the log? Does it just make math simpler, or is there a reason?
It makes it much simpler, yeah. And eventually it's going to be mutual information, so I need the log.
Okay.
So ik is going to be either 0 or log the size of L, which basically means I don't need to label more than one variable. Once I did one, I know everything, which is probably your intuition. But there could be more interesting cases. Here is one case. Think about the chain structure in ranking problems. Right? So basically I have 2 labels, less than or greater than. Given n items, there are n choose 2 labels that I need to assign, all pairwise comparisons. And if I gave you k of them, it becomes a partial order problem, right? So think about it this way. I have these 101 variables there, and I gave you just these 3 orders. It leaves a lot of options. Now, in fact, to compute ik, really I need to count linear extensions of these partial orders. We don't know how to do this. There's no closed form as far as I know, but we can use simulation and study ik this way. Now, think about this. This is a very similar case to the temporal order, the timeline order that I discussed before. In fact, the temporal order, or timelining, as we call it in NLP, is a little bit more constrained than this, because in addition to temporal order, I also have this statistical constraint on what event could come before others and what could come after. But this is a pretty good approximation that is easy to study for the temporal case. I can think about other examples. Bipartite graph structure in assignment problems. So what you will have here is you'll have the agents, and D prime tasks, which are really going to be my labels. And my goal is to assign tasks to agents with some constraints. Only one task to each agent, no tasks gets 2 assignments from 2 agents. And again, if I think a little bit about it, there is a closed form solution to IK, it's this one. And again, this is a type of structure, a relatively constrained structure that you can think about other problems in NLP that will be not unlike this. Finally, last example is a very typical problem in natural language processing, BIO structure in sequential prediction. BIO stands for begin, inside, outside. Typically when we think about chunking, shallow parsing, name entity recognition, this is one of the conventions that we use. So every token in the word I'm going to label with either B or I or O. And of course there are some constraints. For example, O cannot be immediately followed by I. If it's not an O, it has to be a B there. So I have some constraints. And again, I don't have a closed form solution to IK, but we can do simulation. So what can we conclude about this IK? It's a concave function. So IK minus 1 is decreasing. And I'm giving you here a few examples of IK minus 1 shifted so that they'll all start from the same place. If there is no structure at all, it's the one at the top. I gain nothing. And as you have more and more structure, more constraints, more expectations on the output, you see a steeper slope. So the slope may be an indication to the tightness of the structure. And what we see is that when we annotate structure, it gives us an idea of how much benefit do we get from a new label. Essentially, it gives us a tool to quantify the benefits of partial signals. In the general setting, we can think about IK. So this was an instantiation. Really, you can think about IK as an mutual information between the structure and its annotation. And I'm using an entropic notation here, and this is why I needed the log. So I think about a K partial annotation as a vector of random variables with one additional symbol, which is the no label yet symbol. And then I have a joint probability distribution over the Y, the assignment, and the partial annotation. And we can show that IK is really mutual information between AK and Y, where both are labeling using the uniform distribution. So why is this important? So in the structure prediction context, where which I showed in the few examples before, the mutual information analysis really provides a view of the structure annotation. It says this is the reduction in the uncertainty of the target structure as a function of this process of annotation, of partial annotation. As I annotate more, how much do I need more information? But more generally, every signal that has non-zero mutual information with Y can be viewed as annotation with just tweaking the notation from the partial case to the more general case. So basically what I'm saying is that for all the partial signals or all the signals that I hinted on before, it really gives me a way to understand and quantify the value of the incidental signals using this tool. I can measure what benefits I'll get from them, and I can maybe order them, and eventually, which we haven't done, I can even study which signals I want to work on getting and which I don't, which order I want to get them, and so on. So that addresses one aspect of the problem that I wanted to address. There is still the algorithmic question. And I want to say two quick things about algorithms. So algorithm implication 1 is going to be an algorithm. Now, this objective function is kind of the standard objective function of structured prediction, where on the left side, you have your learning. I'm writing it here as a linear function over phi of xy, functions over the input x, the output y, but you can put any function that you want there, you can put your favorite neural network there, and the important thing is that the other side, the c of xy, is knowledge structure constraints that I want to impose on my structure. And this is really the objective function that drives algorithms like posterior regularization, PR, from Tasker's, Ben Tasker's work, or constraint driven learning from our work. Basically drives a constraint EM algorithm that learn with the left component and impose knowledge or constraints with the right one. And we can do this also here. So I'm going to show here a kind of a skeleton of bootstrapping with constraint. Essentially, we learn with whatever data there is, partial annotation. And then we recurse and at every step, or iterate, and at every step we use inference, which means we enforce the constraints. We want the output to satisfy our expectation, to be coherent given the knowledge that we have, and then we keep on going. So you can think about it as self-training or bootstrapping, only that in each intermediate step, you impose the knowledge that you have. You want your model to behave well according to your expectation. So we've done this, for example, in the temporal domain, where we impose these constraints using an ILP formulation, an integer linear programming formulation. And what you can see is very significant improvements in identifying temporal relations between just bootstrapping versus bootstrapping with knowledge. So again, this is another piece of evidence, there's a lot of it, where knowledge incorporated into the learning actually is more powerful than annotation. And this can be quantified. I mean, we can generate graphs that show every piece of knowledge, how many examples is it worth. So that's one aspect, one algorithmic aspect. Here's the second one that I think is interesting. So let's assume that you have a fixed budget for annotation. Your crowdsourcing mechanism or anything else, or maybe an abstract notion of fixed budget. You can either annotate M complete structures, N labels each, or you can annotate M times K structure partially, N over K label each. Which one is better? So again, the tools that we've developed allow us to address this question. And clearly, we know now that it's going to depend on the tightness of the structure. This is the stuff that we just discussed before, and of course the algorithmic approach that we're going to use. So here is the game we're playing here. So I want to be able to annotate this graph, the green graph. I have two options. Either I'll annotate a small number of complete graphs and leave these empty, unannotated, or I'll annotate a larger number of graphs, but partial. And eventually I'm going to test on everything. I'm going to learn models in these two scenarios. I'm going to test on everything and see what happens. So here is what happens. In the temporal domain, where I have a pretty good understanding of the structure, right? So I told you that there's transitivity, but there's probably there are also statistical constraints on consecutive events and so on. You can see that, of course, when I annotate everything on the right side, everything is the same. But in the middle, actually, I gain a lot of advantage from partial annotation. Here are two other problems. Semantical classification, which is a sub-case of semantical labeling. For those who know, I get some gain in the middle, not as much as here, just because the problem is not as constrained. And in shallow parsing, I get a little bit of advantage, not statistically significant. And again, the reason is that there's not a lot of structure there. It's almost independent decisions. So again, the bottom line is that in many cases, it's easy to get some good signals, difficult to get exhaustive annotation, and we want to be able to ask the question of how can we use it, and how can we study this in a more principled way. And we've done this in many cases, recently in transliteration, where we use this in the context of, Our learners are neural networks, but we impose constraints. We used it in the context of name entities, temporal relations, and a few others. So the bottom line is that these signals, these weak signals, can be thought of as partial annotation in a well-defined way. Okay, so that's basically what I wanted to say about signals and structure. So the usefulness of these signals is a function of the tightness of the expectation we have from the output. The more we know about what's going to come or how should it look, the more useful weak signals are going to be. And of course, as I said, there are many questions that one can still ask about this framework. So I want to say a few things. I'm a little bit tight on time about behavioral level feedback or end-to-end learning. So I'd like to think about it from the perspective of psycholinguistics, so how kids learn language. So I think it's useful to take inspiration from this. This is a line of work that we developed together with Cindy Fisher, a psycholinguist at Illinois, for quite a few years now. If you think about it, these kids have a really tough problem. I mean, they get this nonsense signal, Topid, Rivod, and Mark blocks, and they see images, and eventually we expect them to learn language. So what we actually know already is that, well, they see it many times, they hear it many times, and it's well established that using cross-situational observations, kids can quite quickly identify nouns. I think about this as the representation plus expectation that I talked about before. However, it's much harder to understand verbs or predicates in general, because there's a lot more ambiguity. If you look at this scene, what should this toddler think about? Is it a chase scene? A chases B, or is it a flee scene? So I think there has to be some feedback, some behavioral feedback that is needed. So here is my favorite coffee example that is inspired by this. So I want to be able to talk to a robot and tell them how I like my coffee. Now, in order to do this, there has to be some intermediate representation, perhaps a meaning representation that this robot understands. I'm going to say it in English, they'll understand and prepare the coffee. Now, how do we do this? How do we recover this meaning from the text? So standard example machine learning give me a lot of pairs of English sentence, comma, semantic representation. That's not going to work. It's not scalable because the teacher, the one that generates this data, really need to understand the agent. And I'm going to talk to multiple agents. I want to talk to these coffee-making agents, but also to my PowerPoint, and also to other agents. Each one of them speaks a different language. No way that we can annotate and hope for good here. So I think we need another approach, which I call response-driven learning. This is the name that we coined. Recent works call it learning from denotation. Same thing. The idea is to exploit the indirect signals in the interaction between the learner and the environment or the teacher. So what do I mean by that? Let's assume that I can initialize, I have a program that can initialize this intermediate representation. And I'm going to send it to this robot, and the robot is going to act on it. They can either say, I don't understand what you're saying, or they can attempt to prepare the coffee. It could either be excellent, it could be very bad. I'm going to give them feedback at the level of the quality of the coffee. And the question is, can we rely on this level of interaction to provide supervision, propagate it back, so that eventually we can recover this meaning. We can learn this transformation and do it. So I'm not going to give technical details here, given the time, but there's a lot of work in this direction. We started it around 2010, but there's been a lot of work. I assume that several of you here are familiar with work on semantic parsing. I think in many respects, it's very similar to the stuff that I talked about before. I mean, these are weak signals that we have to figure out how to use what signals are important, what signals are less important, and how to develop algorithms that use it. We don't know how to do it yet. I mean, we can get some results, we can write some papers on this, but we don't know how to do it. That's the bottom line. So let me finish with a couple other examples that I like for you to think about. So one of them is good old co-reference problem. Here is a problem. The bee landed on the flower because it had pollen or it wanted pollen. And the question is, what is this it refer to? And it's easy for you to figure out that if it's had, then it's the flower that had pollen, and if it's wanted, it's the bee that is the it. Now that's a very easy problem. In fact, you can solve it today because it's only lexical knowledge. You can Google combination of words and you'll get it. But think about this, goes beyond lexical knowledge. John Doe robbed Jim Roth. He was arrested by the police. This is a much, much harder problem, even though at some level it's similar. Why is it harder? Because here you need to know a more abstract thing. You need to know that the subject of rob is more likely than the object of rob to be the object of arrest. This information is not in the sentence. You cannot Google it. You really have to develop abstract representation and then take statistics over this. Much harder and very interesting. My last example, this is a problem that you solved a few years ago in 3rd grade or something like this. John has 6 books. He wanted to give them to 2 of his friends. How many will each get? You can solve this. You can solve this even if I change, give them to share them with. It's a different problem. You can even think about the fact that the reason you can solve both of them with only this minor change is because I use 6 here, and 6 is divisible by 2 and by 3. Had I changed this 6 to 8, one of these interpretations would not hold. You can do all this reasoning, and these expectation or constraints that you have help you to think about this problem. But what I want you to think about is, how do we supervise for these problems? Clearly, straightforward supervision, give me 10,000 problems with the solution is not going to work. We have to think a little bit beyond that. So with that, let me summarize. I try to give you some recent samples from a research program that tries to address some of what I think are the key scientific and engineering challenges between us and natural language understanding. I focus today on incidental supervision, basically how to utilize hints in the data to infer and amplify supervision signals. I looked at it from multiple perspectives, and I also try to provide some initial steps toward the theory of incidental signals, something that will allow us to quantify their value and to quantify using them. And in particular, I think one theme that hopefully came across is the importance and effectiveness of using knowledge in learning. Thank you.
Okay, let's do 1 or 2 quick questions, but you're a bit out of time. Anyone? Oh, yeah.
Okay, thank you. That was an excellent talk. I'm glad to see that this is where we go now. But going back to one of your first slides where you had that really like, bring me some water, it was nice to meet you, something like that. So I'm guessing, okay, like we as humans, we had that balance between what would be, how we would read a sentence and the fact, like our prior expectation that you want to communicate a meaning. So we had that bias that you want to say something to us, so we're going to interpret this. And okay, you talked throughout the entire talk about those biases and the like hints in the data, how they can help us. But are you, or I guess that's the holy grail here, how we could automatically infer which biases in the data would be the most useful ones according to the task that we have?
So I'm not claiming I have a solution, but
I'm guessing that's like where this should, like that discussion could be going. That if I have a task X and there's going to be an infinite amount of biases that can help me solve this task, how would I be able to automatically choose one of them, or as a human,
So by the way, I like to think about it not as priors, but rather as posteriors, which are expectations that I have from the output. And by the time I learn, I already have seen a lot of outputs. And I have statistics on what outputs make sense and what outputs do not make sense. So when you think about developmental psycholinguistics, kids have expectations on what makes sense. They have affordances. They have knowledge about containment. They have knowledge about sort of if this person is here now is likely to be here next seconds too. So there's a lot of things that we learn, and specifically in the context of natural language understanding, there's a lot of statistics, if you want, that you can take without any supervision just by reading. This is encoded in the newspaper article that you read. This is encoded in Wikipedia. This is encoded in communication patterns that you have. You get used to the fact that people present information this way, and this gives you signals. Think about the Chicago hair example that I gave you. I didn't supervise you for this, but you read enough text with things that you know, and therefore when some of the entities are unknown to you, you expect the same conventions to dominate and bias your inferences.
No, I agree completely with that. What I'm trying to ask is that, okay, say the child has expectations, but these expectations were formed from the signal, from the input that it got from the day it was born. So, going back to that example about inferring from the news article something, you went to Freebase or Wikidata and then you gathered a large amount of data and then you figured out that this gave you better results. But how would you automatically be able to say, I don't have to go to Wikidata and look at these persons, to the system be able to decide that, oh, it's a person, so I must be doing that sort of subtask to inform my main task.
What's bad about going to Wikipedia? So think about you reading a new piece of text, and you see a name that you don't know, and you want to know, what is this person doing? It makes sense to me, actually, to say, well, I've seen these kind of contexts before for this person. Let's see what this person does. And you say, okay, so they share their semantic type. So it seems like a reasonable approach to me, even for you doing it, right? So you basically develop some expectation from stuff that you've done, unrelated to this specific task, and you find ways to use it in the current task. So again, there is a mix here between art, what signals are there, how do I exploit them, how do I invent them, and machine learning or math of how do we develop a theory of what signals are going to benefit me, in which order do I want to look at them, how do I quantify their benefits and so on, which I tried at least to build the beginning of a theory for. Not arguing that this is solved, but arguing that this is a necessity, because we're not going to make progress in natural language understanding, the real natural language understanding, nor in the real computer vision. Forget identifying cats and identifying chairs and faces. Understanding that, if I move this cup a little bit more, you know what's going to happen. You will not be able to do this with standard supervision. We have to think about other ways of acquiring information to supervise our programs.
Okay, let's thank Dan again.